horror continue. Millerite and nickel sulfide, oh blah blah blah. Okay. Nickel 2 sulfide to nickel 2 oxide. So I've got nickel 2 sulfide to nickel 2 oxide. How did I come up with those formulae? So nickel's 2 plus, oxygen's 2 minus, crisscross to get me NiO 2, because we're using the crisscross method, and then just to factorize it down to the lowest common what's it's NiO. So I'm doing it in air. The first step in extracting is to roast the ore in air. So I'm going to add that to oxygen, I suppose. And let's see what we can do. Well, the sulfur has to do something, doesn't it? It can't just disappear. So I suppose we're going to be making sulfur dioxide or sulfur trioxide. I'll go with a sulfur dioxide. Actually, if I went with sulfur trioxide, that would be easier, because then I would just have to put a 2 there. I feel rather smart. Is that right? No. How is that not right? Because they say it makes sulfur dioxide and not sulfur trioxide. How would you know that? So I just think that's wrong. Because if you have excess oxygen, you're burning it in air, that's a pretty big excess of oxygen. You would make sulfur trioxide. It's not in the notes or anything. Oh man. Well, they put sulfur dioxide and balanced it out. I don't think that's right. Few seem to realize, yeah. 4B. Oh, this is wordy. Okay, so I've got nickel with 4 carbon monoxides attached and iron with 5 carbon monoxides attached. How can I separate them? Well, they're both gases, so I would imagine that both of them would diffuse at different rates. If you heated them to the same temperature, the lighter one would diffuse faster. So I would say by different rates of diffusion. Plenty of answers, including that one. Different thermal stabilities, boiling points, solubilities, surface affinities, yeah, any other valid answer. I bet they also have different magnetic properties as well. So rate of diffusion, that's my answer. So different rates of diffusion. Rates of diffusion differ. Next one. Okay, so we're doing some entropy change. I'm sure we're going to do S and H and G, and the classic tricks are going to come up. All right then, so I'm just going to write down the values for entropy underneath. Nickel is 29.9, carbon monoxide is 197.6. I'm going to multiply that by 4 because of that coefficient. And nickel, what's it, is 313.4. So if I want to know the change in that, I'm just going to have to do products minus reactants. So it's the sum of the products minus the sum of the entropy values of the reactants. Minus 506.9. So minus 506.9. 1 decimal place should be kept because everything in the question has 1 decimal place. Is that right? And so our first little tricky trap's coming up is that's joules. In fact, it's in joules per Kelvin. And I bet that joule is going to cause us trouble later. Units weren't required for the answer though. Next, calculate delta H. So this is a classic SL question. You've got to write down the heat of formations. Well, they've given me the value for carbon monoxide, minus 110.5. Again, not forgetting to multiply that by the 4. The nickel tetracarbon monoxide jobby is minus 633.0, but they've not given me the value for the nickel. Oh, okay. You look in the data booklet, it's not there. Some kid put their hand up on an exam and I was called in from like another room, which you should never do. It's not in the data booklet. No, it isn't. The heat of formation of any element is 0. Or allow me to just elaborate. So the heat of formation of nickel, solid. Okay. So I've got to make 1 mole of nickel from the elements in their standard state, which of course is 1 mole of solid nickel. So what's the energy change going to be for that reaction when nothing happens? Nothing. It's nothing. Again, we're going to do products minus reactants. If you have the time, you should write out the fact that you're doing products minus reactants. So minus 633 products plus 4 times minus 191. That's kilojoules per mole. Sure, we've got that there. Actually, kilojoules. Oh, it says in kilojoules. Would I have lost a point for screwing that up? No. Don't think so. Next up, use your answers to work out. So that they want to know when will this reaction start to go backwards? At which time will the liquid decompose into, so when will that start going backwards? So when will the forward reaction start going backwards? So that's a bit of a heavy-handed hint that, so when is equilibrium going to kick off? So when delta G equals 0, you are at equilibrium. I've also got a value for delta S, I've got a value for delta H, and they're asking me about temperature. Delta G is delta H minus T delta S. Isn't it just that? I'm putting the numbers in. I'm going to cheat. Yeah. Little tricks. Here we go. So that's going to be 0. That's not a trick. Delta H was minus 191. That's not a trick. Temperature's T. Now that delta S, we've worked it out in joules. And we need kilojoules, so you're going to have to divide that by 1,000. So multiplied by minus 506.9 over 1,000. This should give me a temperature, which is when the equilibrium kicks off. Forgot that 0. Okay, let's do that calculation. So my temperature is going to be looking like 3 sig figs there. What was that? 377 Kelvin. Are they messing me about with temperature units or anything here? Yeah, in degrees C. There's no end to these cheeky little tricks. Okay, so now I'm going to take off 273. Take off 273 and that should get it for me in degrees C. So that's going to be 104 degrees C. Is that right? Yeah. 4D, 50% got it right. Why are you messing around with carbon monoxide? Isn't that hazardous? Yeah. It's toxic or poisonous. Well, what a dumb answer. It's hazardous. Why? It's toxic, poisonous. Okay. They say it could catch fire. That's true. Well, actually explained. Stops you breathing properly. Stops the blood working. And they say that you should be aware of the difference between suffocation and poisonous. Am I even aware with that? What a random thing to tell kids to be aware of, the difference between suffocation and poison. It's not even in the kids' syllabus. Next up, 5A. Few noticed the missing lone pair. Yep. Another cheeky little trick there. So I'm going to pop that lone pair in right now before I even read the question. Two hydrides of ammonia, blah, 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 blah. Estimate the bond angle H in C. H in C. So they want to know H and C. So this bond angle here, well, that looks a bit like ammonia to me. So I reckon that's 107.5 degrees. I'll tell you why. Because the central atom has 4 electron domains, 1 lone pair. So it's going to be 107.5. You can accept that? Yes. Next question. The electron domain geometry around the nitrogen atom and its hybridization. Okay, the electron domain geometry around the nitrogen. So not the bonds, not the shape of the molecule, the electron domain geometry. And the electron domain geometry, well, I can see 1, 2, 3, 4 electron domains. So the geometry is going to be tetrahedral. Tetrahedral. And the hybridization, well, I don't see any pi bonds there, so that's going to be sp3. Is that right? Tetrahedral sp3. Great. C. If you recognize the H plus and the OH minus. Ammonia and ammonium almost cost me my career. When I was doing A-levels in England 32 years ago, my teacher never taught us ammonia or ammonium, and the whole paper was just devoted to it. So I got everything else right, luckily, I assume, because I still got a good grade. But whole chunks of it I didn't understand. Explain the effect of adding H plus ions on the position of the equilibrium. Well, naively, you might think adding H plus ions has no effect because I don't see any H plus ions in the equilibrium. But you'd be wrong, because the fastest reaction in nature is, chemical reaction, is H plus and OH minus. So what happens if I add H plus ions, I'm going to start removing these OH minus ions. And so if you stress a system in equilibrium, it's going to move to oppose the stress. So it's going to shift to the product side. So it's going to shift to the product side to replace the lost hydroxide. That's what I'd say. Yep, that's right. Shifts to the product side to replace the stress of losing the hydroxide ions. 5D. calculate the pH. So since it's kind of like an ammonia-based thing and it's making OH minus, at the end of all of this, I want to make sure my pH is above 7. If it isn't a number like 8, 9, 10, 11, 12, then I've cocked it up somewhere. Maybe I did the pH. So maybe I did the POH instead of the pH. I'll mess something up. So I have to keep that in my head. How many points is this worth? 20? 3 points. All right, 5 minutes. Here we go. So you've got to write out the KB, the base dissociation. So I've got N2H5 plus and OH minus divided by N2H4. So all I've done is I've just written that out as an equilibrium. Now you might think, what about the water, Thornley? The water's in there. Well, rather delightfully, that water has gone into there. Now normally that's Kc, equilibrium constant, but if you turn it into a B, that means you've secretly hidden the water in there. So don't worry about it. I'm also going to assume that at the top row, both of those things are equal. I'm going to assume that the concentration of this malarkey is the same as that concentration. Why is that valid? Well, because for every one of these made, I make one of those. So within reason, that's valid. And I always think that the number on the bottom is the number written on the bottle, the concentration on the bottle, which is 0.0100. Okay. Now my value for KB, do they give me KB? No, they give me PKB. So the PKB is 5.77, so KB is 10 to the minus 5.77. Nasty. Well, let's work out OH minus. So the concentration of the OH minus. 1.29. Let's keep 4 sig figs. 1.293. So 1.293. Did I miss an exponent there? Oh yeah, geez. Times 10 to the minus 4 moles per decimeters cubed. So is it the pH I want? Okay. So now using, I'm going to work out what the POH is now. Using POH equals negative log OH minus. So let me work out the POH. So negative 3.89. So the POH is 3.89, and I know that a pH and POH is 14, so that gives me POH is 10.11. Maybe stick to 3 sig figs. Is that right? Yeah, that's right. And that feels right to me. Yeah, that feels right. Next one. Suggest a suitable indicator. Hydrazine and sulfuric acid. Well, let's have a think about the graph. So if I have hydrazine and sulfuric acid, come on. Let's say that's a pH, and let's say that's volume of, well, let's add acid. So it's a strong acid, hydrochloric acid, and a weak base. So that means it's not going to be this broad one like this. That's strong and strong. It's not going to be, oh, hold on. That was upside down. It's not going to be this one. That's the strong and strong. It's not going to be this weedy one. That's the weak and weak. It's going to be shifted towards the strong acids, shifted towards the lower pHs. So it's going to be something like that. So maybe 7's going to be about here, pH 7. So the point of inflection is shifted down towards the strong acid. So we shifted towards the strong one. So let's have a look at the so I'm going to want an indicator that changes colour below 7. I think below 7 is probably where I want it to, because it's been shifted down. So here shows the pH of where they'll change colour, so below 7. So I'm going to say bromocresol green, bromophenol blue, methyl orange, any of those three. Yeah, I'm feeling smart. Got like 10 right in a row. Yeah. So any of those ones. E. Magnesium powder is added to ammonium chloride. Very few people gave an observation. I've never heard of this equation before. Magnesium, I'm not going to look at the answer. Let me see if I can do it. Magnesium powder is added to ammonium chloride. Okay, so magnesium powder is added to ammonium chloride. So I really don't think there's much to be done here. I've got a neutral thing and a plus and a minus thing. Am I reading it right? So what's observed? I have no idea. I'm going to make a guess. The magnesium dissolves. The magnesium disappears. How on earth was I supposed to know that? The equation, the chloride doesn't do anything. The equation, do you have to give the equation? You do. I mean, I don't know what I'm missing here. Magnesium 2 plus 2 ammonia plus H2. I have no idea where that comes from. Do not accept this, that, and the other. The equation must be ionic. They have a backup answer, which I think is the right answer. So this is what it is. Ammonium chloride is acidic. Ammonium chloride is acidic because it's made from a weak base and a strong acid. And so it goes with the strong one. It's made with a strong acid, so it's going to be acidic itself. So if ammonium chloride is acidic, then Mg plus H plus, okay, magnesium dissolves in acid. That I can do. Magnesium 2 plus hydrogen. That one makes sense to me. Allow that. That's the right answer. This is brutal. The top equation, I have no insight into what they're trying to do there at all. No idea. The second one makes sense to me when I cheated and looked at the answers. Many struggled, yeah. F, determine the enthalpy change of reaction. Okay, so this is bond energy. They're telling me to use section 11, and section 11 is bond energy. So like you, I know I can do bond energies. I can do them. Can I do them without making a silly mistake? Let's find out. So looking at the molecules here, N2H4, so I've got 5 plus 5 plus 1 plus 1 plus 1 plus 1. I'm adding up the valence electrons, dividing by 2, so that's going to be 7. So I need 7 lines. 7 lines. Each line represents a pair of electrons. Is it single or double bond here? 1, 2, 3, 4, 5, 6, 7. So it's a single bond. Every hydrogen has 1 line, pair of electrons, and every nitrogen should have 4 lines, 4 pairs of electrons, stable octet. Now they're trying to see if I'm stupid enough to not realize nitrogen has a triple bond, and also do I realize that I have to account for the fact that there's 2 hydrogen bonds to be broken. If you set it out nicely, you got plenty of chance for partial credit if you mess it up. All right. So the way I do it is on the reactant side, I'm breaking apart the molecules, so I have to put in energy. So that's going to be positive values. And on the product side, I'm making bonds, which releases heat. I can feel the heat on the cheeks. So that's going to be exothermic, so they're going to be negative. And then what I do is I just sum everything up. So sum everything up. Minus 95. The IB does like it as well if you sum up the value there and you sum up the value here. Sum those up, and that's normally where the second or third point is. My God, it will be like midnight by the time you got this far. 5G. Well, they're talking about I need the equation in F. They've given me another equation and a third equation. So there's 3 equations that are connected by delta H. So that's probably going to be one of those kind of Hess triangles, isn't it? In fact, what they want to know is this unknown here. That's the delta H that's unknown. Excuse me. The standard enthalpy of formation is 50.6. So making 1 mole of that chemical is 50.6 kilojoules. Standard enthalpy of formation is the energy change when you make 1 mole of a substance from the elements in their standard state. So the standard state is going to be N2 for nitrogen and a couple of H2s. Now looking at question F, that is the equation in question F. And that, what was the value of delta H for that? I worked it out, didn't I? Minus 95. So that's minus 95. Now the rule for these triangles is if you sum the arrows going clockwise, it equals the sum of the arrows going anti-clockwise. But this is unusual because all the arrows are actually going in the same direction. So what does that mean? That means they all add up to 0. I could rearrange this weird equation here. That arrow minus that arrow equals 0. This is Hess's law. The energy change for a reaction is independent of the pathway chosen. So following that adds up to 0, I've got my delta H, the unknown one, plus minus the 95. plus 50.6 is 0. So that gives me delta H is 95 minus 50.6. Oh, lazy. I'll do it on a calculator. So that's plus 44.4. And what they want in kilojoules per mole, or kilojoules per mole. I'm not going to spend any time with the sig figs or decimal places because they've screwed it up before in the paper, so it's not my concern. Plus 44. So even though I added an extra sig fig, that's okay. You're allowed to be 1 out in either direction. 5G's done. 5H. This is just a stoichiometry question tied up in a bit of a knot. Not too bad. So my oxygen, I've got 8 thousandths of a gram in a decimeter cubed, and I've got 1,000 decimeters cubed. So that means I have a mass of 8 grams. I like to use the boxes method. So that's moles, mass, molar mass. I also like to put the units in case I forget later, and then I'm covered myself. The molar mass of oxygen is 32, not bothering with decimal places, and so moles is mass over molar mass, so that's going to be 1/4. The question wants to know the value of that box, the mass of N2H4. So the molar ratio is 1:1, which means it's 0.25 to 0.25. What's the molar mass of N2H4? 4, 28, 29, 30, 31, that's 32. Oh. So mass is moles times molar mass, so that's going to be 0.25 times 32. We're just back to 8, aren't we? Isn't that simple? 8 grams? Yeah, 8.0 grams. Okay, getting a bit fast and loose with those sig figs. Calculate the volume of nitrogen formed. It's only 1 point, so it can't be that tricky. Well, I know that I've got 0.25 moles of nitrogen because, again, the ratio is 1 to 1 to 1, 0.25 to 0.25 to 0.25. So if 1 mole of gas is 24.8 decimeters cubed, what about 1/4 of a mole? Okay. So I know that I've got 0.25 moles and that 24.8 decimeters cubed is 1 mole. So how many decimeters cubed do I have? 6.2. 6.2 decimeters cubed. Yep. Okay, they're lulling me into a false sense of security. Hammer's going to fall. Here's the orgo question. All right, 6A, only 30% of people got this correct. So this is the initiation, propagation, termination. Have they tipped you off about that? They do later on in the question. Often people forget. This is an SL concept though. So the type of reaction, well, I'm swapping out hydrogens in ethane for chlorines. So it's a substitution reaction. Substitution. And remember, the ultraviolet light breaks the chlorine in 2 to make radicals. So the mechanism, I think, is a free radical mechanism. Yeah. Okay. Next up, a couple of propagation steps and a termination step. Well, there are probably 50 propagation steps. So I'm going to try and choose the ones the IB are going to have in the mark scheme. You're never going to get an H dot. That's why I put a cross through it. So whatever propagation step you've got, it's going to be no H dot. All right, so I suppose I've got my ethane. And remember the chlorine was split in two to make Cl dot. There's not really much that can happen there, is there? If I don't want to make H dot, there's really only one thing that can happen in this case, which is I make HCl and I leave that dot, that lone electron behind. So that's one. That's one propagation step. So propagation, a radical goes in, a radical comes out. Let's try another one. Well, let's say I've got this CH3 CH2 dot. That's just another way of writing that. And let's say that bumps into a chlorine. I've got a chlorine dot, and then I've got CH3 CH2Cl. Those are my two propagations, and a termination step. Well, the easiest termination step is there's two Cl radicals bump together and make chlorine. All right, there's my points for that. Next one, poorly answered. Oh, H1 NMR splitting patterns. I kind of like that. So let me draw out the molecule, chloroethane. So H1 NMR only tells you about the positions of the H1. How many hydrogen environments do I have? Well, I see two hydrogen environments. I've got these three hydrogens here. I've circled the carbon, I didn't need to do that. These three hydrogens here are in one environment. So that's going to have a peak of, with an area of 3. And I've got these two hydrogens here, which are in another environment. So that's going to have a peak of area 2. But I don't think that's what they were asking. They want to know the splitting pattern. So the splitting pattern, you have to count the hydrogens on the adjacent carbon and add 1. So looking at these hydrogens, let's try and keep some colour consistency. Looking at these hydrogens, the adjacent carbon is that one. How many hydrogens on that one? 2, add 1, 3. So this split is going to be into 3. It's going to be a triplet. Using the same logic, I read somewhere that the guy that invented the MRI, which is the same machine, he scanned himself and he had a life-threatening condition. Saved his own life from his own machine. Nice. For these hydrogens, the adjacent carbon is that one. How many hydrogens on that? 3, add 1, 4. So that's going to be, is it called a quartet or quartuplet? I think quartet. So to answer the question, for 1 point, it's a triplet and a quartet. Triplet and a quartet. Nice. That's my points there. On to TMS, tetramethylsilane. Why is it a reference standard? Multiple reasons. It has a low boiling point, so you can boil it off of your substance easily. I would also think that's probably what's more important, is it has a very strong peak because it has 12 carbons, 12 hydrogens in the same environment. So it has a very strong peak. And that peak is also distant from most of the other organic chemicals you're looking at. Well, what's moving that peak away from everything else is that silicon, isn't it? So that's 2 points. What else do I know about it? And it's not split. It's just one single peak, so it's quite easy to line up and get it just where you need it. Okay, I've got my points for that. Next up. Empirical formula. 75% of the people got this right. So I like to put a big C, a big H, and a big Cl, representing the 3 elements. I put the molar mass underneath. Again, I've lost my patience with the sig figs. and the mass or the percentage on top. So that's about 24%, that's about 4%, and that's 72%. Okay, so that gives me C2H4Cl2. Don't stop there, you're after the empirical formula. So divide everything by the smallest, which is 2, and that gets you CH2Cl as your empirical formula. Yep, 2 points. Next up, I remember reading the IB said that people thought this was 2 chemicals. It's the same chemical. It was confusing people. So I've got the empirical formula here. So the molecular formula, the actual formula of the actual molecule, it could be that, it could be double that, triple that, quadruple that. Let's try and work out. The mass spectrum, well, that tells me I need to look at the molecular ion. That's the molecular ion, which is about 100. So the actual molecule itself has a mass of about 100. Now, how much does my empirical formula, what's the mass of that? 12 plus 1 plus 1 plus 35.5, let's say 35. It's 35, 36, 37, 47, 48, so that's about 49. So I can see that 100 divided by 49 is near enough 2. So that means I need to double my empirical formula to get the molecular formula. So it's going to be C2H4Cl2. Doubled that. Well, there are 2 isomers of that, aren't there? There's the 1,1-dichloro and the 1,2-dichloro. Let me write those out. So I could have the chlorines on the first one, or I could have the chlorines split between the first and the second. So I suppose I better work out which is which. I'm going to use the H1 NMR to do that since it's there. All right. So there'd be two peaks on the H1 NMR with area 1 and with area 3. And over here there'd just be 1 peak, but with an area of 4. There's 1 hydrogen environment there, and these 3 are in the next hydrogen environment. So what have we got on H1 NMR? Well, there's 2 peaks, isn't there, with a 1:3 ratio. So since there's 2 hydrogen environments, I would say it's going to be 1,1-dichloro, ethane. Is that right? 100, la 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 la, 2 signals. Dichloroethane. Yeah, that's enough for your 3 points. 6C, III, few correct answers. I have insight into why this is incorrect. It's not on the syllabus. This is an elimination reaction. That was removed. This syllabus doesn't have it on it. I checked through the examiner's report. They didn't admit that. They just said few correct answers. This is dishonest. I could take a guess. Hot alcoholic solution, that's elimination. So what on earth is going on? I make chloroethene. It's a nucleophile, yeah, okay. What else could the NaOH be doing? I don't know. It was 10 years ago since they asked syllabus. My guess is it's a base. Yeah, it's a base. What a waste of everyone's time. That should have been struck from the paper. Off syllabus. 6D, polymerization. Draw a section of the polymer. So I always like to start with ethene. I've got my 3 ethene molecules. Poly means many. Polydactyl, many fingers. Polytheus, many gods. Polyorchid, many testicles or ovaries. Polynomial, la-di-da. So I've got my 3 there. And so what happens is this bond breaks, half goes this way, half goes that way. That bond breaks, half goes that way, missed. And half goes that way, this bond breaks, half goes that way, half goes that way. And now I'm going to fix it up by putting the chlorines in. So there was a chlorine there. Let's put it at the bottom. Why not? Doesn't matter. Okay, that's my point there. They're fussy. You've got to have those bonds coming off at the end to show that it isn't terminating there, that it carries on. 7a, few were able to do this one. Oh, we're on to the next one. Benzene is an aromatic hydrocarbon. Discuss the physical evidence. Now, to me, physical evidence means physical properties, boiling point, melting point, stuff like that. But the boiling point and the melting point tells you about the intermolecular forces. So I must admit, I did look at this question before, and my best guess was, if in doubt, just say that benzene has the same length carbon-carbon bonds and the same strength carbon-carbon bonds. And that's almost always the answer. And I know that's right. All the same length. But they don't give it to you for strength. Isn't that interesting? So it's one point for saying that all the lengths are equal, and then you could say the bond angles are equal, or that if you shone X-rays at it, it would show that it's planar. I mean, these are things you probably knew about benzene, but the question wasn't that clear to me. Okay, so they're not giving you a point for saying that they have the same strengths. Let me check the secret bonus answers they sometimes allow. No, don't like that question either. All right, same bond angles, same lengths. Okay, so the reaction between benzene and bromine and cyclohexene and bromine. So my benzene here. Now benzene, you break that ring, it's going to remake it. Benzene likes to substitute, likes to swap out hydrogen for whatever you've got, but you're not going to be breaking that ring apart. You're going to retain those notional 3 double bonds there. So if I add bromine, what's going to happen is I'm just going to swap out a hydrogen on the ring for a bromine and make HBr, substitution reaction. For cyclohexene, well, that behaves like an alkene. And so when you add bromine to an alkene, the double bond breaks and you stick a bromine on each end. So let me add the bromine to that. I'm going to break that double bond and add a bromine onto each side to make the dibromo. How many points? 2. That should be enough for 2 points. Accept correct equations. Oh. So, like I said, this is a substitution because you're swapping, and this is an addition. Well, you're adding it on, you're not swapping anything out there. That was the answer they were hoping you'd get. Next up, a few correct answers for that. 7C, state the reagents used to convert benzene to nitrobenzene and a formula of the electrophile form. Do you know what? I only know this because I did it recently. You've got concentrated sulfuric acid and nitric acid, and then you make that kind of funky NO2+. I know that's right. Wow. Their answer says plus NO2, but they will magnanimously accept the plus going at this side. I mean, this is some university level madness here. I didn't know that the plus could go at the front. Okay. 7D. Explain the mechanism for the nitration of benzene using curly arrows. Yeah, so normally this is kind of like the stinger question. One of the 2 tricky questions they put in when they want to make the exam a bit harder. This is not needed. This is hard enough. Okay. So I've got my benzene and I've got my NO2. I think that's called nitronium. So NO2 plus is an electrophile. It wants to have electrons attracted to it. So the electrons from the ring go towards it. And now I've broken that ring. I thought the ring couldn't break. Well, it can break as long as you reform it. And so now I've got that NO2 there. I'm actually going to take the time to draw in that hydrogen as well. Next step. Well, this the electrons in that bond to the hydrogen that frankly was always there. You know what? I'll just draw it in. They go back and complete that ring again. Fantastic. So now the ring has been reformed. I've got my NO2 and that H dropped off as an H+. I wonder if that's enough for my 4. Yes. There's plenty of ways you could lose points on that. Arrows going to the wrong place. They like to see dotty half circle there with a plus in the middle. There we go. 7E. I remember they did apologise for mentioning aniline. What the hell's aniline? That's not IB. So you probably should have dropped that question. Shouldn't be out of 95. So I want to convert nitrobenzene to aniline. Well, so I suppose your best guess is the only reaction that the actual syllabus has with nitrobenzene is to make this chemical here. Phenylamine, I think that is. Oh my God, I'm going to check it. Okay, Google.
What is phenylamine?
Yeah. So how would I turn NO2 into NH2? You know what? I've no idea. I know that you can add hydrogen with platinum, and that bungs on hydrogen where you need it because that's the SL addition. But that, I don't think that's worth 2 points. No, that would get me 1 point. What they wanted was iron and sodium hydroxide. I have no recollection of that ever being asked before. Okay, so those 2 points there, iron, sodium hydroxide. Next up, 8A. Got some ozone. What I find annoying about this paper, personally, is that there's like 5% of the IB that I can't remember. Maybe only 3% now, after all these years. And there's about maybe 3% that just frustrates and confuses me. I can't seem to always understand what they want. And this whole paper is based on kind of the 6% of the little bit of thin ice for me personally. And therefore the poor kids I teach. 8A, ozone. So nitrogen monoxide reacting with ozone. All right, I'm going to give it my best shot. Well, what's going to happen? I've got to destroy the ozone, haven't I? So let me make NO2. I know that exists, and O2. Great, I've destroyed ozone. Let's destroy some more ozone. Let's say that NO2 reacts with some more ozone. I've got a sequence here. And it says it's a catalyst, the NO, doesn't it? So I've got to have the NO back again, and then I've got a couple of oxygens hanging out there. I know there are multiple equations for this. Okay, so it turns out that they wanted some radicals. Did I get the equations right at least? Yeah. Are they going to take a point off that? The radicals? Allow representation of radicals without dot if consistent throughout. Yeah, okay. They're inconsistent with their radicals too. 8B? Or did they want me to show that the NO comes back out again and goes round? Did I miss that? Well, there are. It's behaving as a catalyst. 8B, why is ozone of international environmental concern? It allows high energy ultraviolet light through, so it allows ultraviolet light to the planet's surface. And plenty of problems with that. Skin cancer, cataracts, immunosuppression. It compromises plant growth. Which ones has the IB gone for? Skin cancer, tissue damage. So they've missed a whole bunch. Missed a whole bunch of them. Immunosuppression. So it frustrates me when there are right answers to this, especially if you've done environmental science IB. You know more answers, I'm sure. Well, we're done. I disliked almost every minute of that. That was, I think, incredibly unfair. It's a big organisation that's put many exams out. One exam has to be the least fair and the worst one. And they haven't set another one like this for a while now. But there we go.